Okay, hello everyone. I'm Eric Holk, and I'm a PhD student at Indiana University, like Lindsay who spoke earlier. And then I'm also a Rust intern and also a repeat offender. So anyway, I'm going to talk to you a little bit about what I did this summer with the message passing system in Rust. So Lindsay mentioned that Rust is supposed to be safe, concurrent, and fast. And my work sort of, actually I guess deals with all three of those, and that message passing is important for concurrency, so you can have multiple things running at once. We want the message passing to be fast, and then we also want to be able to provide some safety guarantees in there too. So to start off with, how many people here are familiar with double buffering for graphics? Wow, that's like everyone. Okay, well you can ignore the next like 4 slides or so. So if you aren't familiar with how double buffering works, the idea is the way that people used to do graphics is you would have a display up there, and then you have some picture that you're drawing on there, and then you draw, and then you can see as it's drawing in there, you might actually see the intermediate forms on the screen, and that's a bad user experience. And so what we, and then it goes back and you can see that again. So for double buffering, what we end up doing is we create this other renderer task that's up there. And then we create a copy of the video buffer, and the renderer task can then be drawing on it, so it draws. And then when it's all done, it sends the buffer back to the display. The display swaps the two, which happens really fast so you don't see it happen. And then the renderer can go back and keep on drawing. And so this actually comes up in sort of one of the biggest projects in Rust right now, which is Servo, in that we want to keep the compositor thread, which is responsible for throwing pixels up on the screen, separate from the renderer. And the reason to do this is to keep responsiveness going, so that while you're handling, say, like a new layout update event or something like that, you can still be scrolling without everything getting jerky. So there's like some problems there that could happen though, and like you need to make sure that you only ever have one buffer at a time, so that there's always a buffer available to show on the screen, and things like that. So we want to try to have Rust help us make this program correct, and then also provide us performance. So here's an example of what the code would look like if you were doing the double buffering in Rust using the new channel contract system. So we have this function called drawFrame, and it takes a channel which it uses to communicate with the compositor. And so the first thing it does is it, okay, there's, you see that? Uh-oh. Okay, I guess you can't see my mouse, so you just have to imagine what I'm saying. Anyway, so there is a channel up there, and we use that to request a buffer. And then we go into the select thing, and we wait for the compositor to send us a give buffer message, which includes a buffer. So then we call the render function on that buffer, and then when we're all done, we release the buffer, so we send it back to the compositor, and the compositor will draw whatever it is you drew on there. It will show it up on the screen so the user can see it. Okay? Is this code clear to everyone? Okay, cool. So here's a slight variation. Can someone tell me what is wrong with this? There's a problem in there.
You use buffer after you move out of it?
Yeah, so I've released the buffer, I've sent it back to the server, and then I go draw on it again, and I try to send the buffer back to the server again, which is problematic because we don't have the buffer anymore, right? So we would like it if Rust would prevent this, and it does. The error message here, that's an actual error message from actually compiling this code. Maybe not the most intuitive here, because really it seems like maybe the error is that we're reusing the channel after we've used it already again. But basically, because we're trying to send a message on the same thing twice, and the protocol says we can only send it once, the compiler gives us an error that we're trying to do something we shouldn't. Okay? So here's another attempt. This time I've decided to request a buffer, draw into it, and then request another buffer, and then draw into that and release it. But this also doesn't work. Does anyone have a suggestion for why? Ben?
The second request on the channel is invalid because the channel was consumed in the first one.
Right. So what I forgot to do was return the buffer to the server, or to the compositor. So I requested a buffer, I drew into it, and then I requested another buffer, without returning the other one. And so now there's not enough buffers left in the system. And I think on some operating systems, you will actually just hang if you do this, because it doesn't know what to do if you forget to return the buffer. In Rust, we get this compiler error up there, which is a little light, I guess. But so it says mismatch type expected a acquire, and instead it got await buffer. So that's telling us that we're trying to send a request on an object that doesn't support the request message. Okay. So if we really want to draw 2 frames in a row like this, then this is what the code ends up having to look like. So we've gone through all the steps of requesting a buffer, waiting for the compositor to send you a buffer, drawing into it, releasing it, then requesting a new buffer, and so we're obeying the protocol and everything is fine. Right? Okay, so I keep saying protocol a lot, and that's sort of a key part of all of this. And so underlying that code example up there is this thing here. This is a protocol specification. And so we defined a protocol called double buffer. And there's a list of states on there. So we've got 3 states and then a set of messages that we're allowed to send in each one. Okay, so there's the acquire state, the wait buffer state, and the release state. And in each of those states, you can either send or receive. So that's what the part after the colon says. And then there's a list of messages that are allowed. So in this case, we're only allowed to send one kind of message in each state, although you could have protocols that send multiple ones. So in the acquire state, you're allowed to request a buffer. And then when you do that, the arrow there says that we transition into the wait buffer state, at which point you wait to receive a give buffer from the other side of the connection. And then that gives you a give buffer message with some sort of buffer type associated with the message. And then you transition to the release state, which says that the server is waiting for you to return the buffer back. And then in the release state, we have a release message, which takes a buffer and passes it on over to the server. If we like pictures, we can draw this out. So I've colored the send states as red, and then the receive states as blue. So we start up there in acquire, we send a request, and then we're in wait buffer. We send release, and then we receive a get buffer, and then we come back to the release state, and then we go around, and we're in the acquire state. Okay? So you'll notice that in all of these, I've described it in terms of sending and receiving, but there has to be the other end of the connection, where every time I send a message, the other end receives, right? So one of the things we create is a dual protocol. And basically, the way you get a dual protocol is you just reverse all the sends and receives in there. And so that the protocol compiler will take that protocol specification and actually produce 2 protocols, which I've drawn here. So there's one where, again, red is send, so we send and receive, then we send. And then there's the other one which would be run by the compositor in this example, where it waits for someone to request a buffer, and then it sends them the buffer, and then it waits for them to send the thing back. Okay? So we take this protocol specification and we run it through our protocol compiler, which generates a bunch of Rust code that provides all the guarantees that we need to make this work. So that means we have to have a module for the client and the server. And then all of the states in the protocol get compiled into Rust types. And then those are, so Rust has an affine type system, which is sort of a scary term for, it counts how many times you use something. And so affine types are things that you can, if you use the type more than once, it will be a type error, okay? So each of these states, once you send a message in that state, you've used that up, and then you have to get somehow like a representation of the next state. And that's how we use the affine type system to support that. We also produce send functions, and that just sort of makes it a little easier to package up the messages and send them. And then message patterns for when you receive. Okay? So we can take this and go back to the code that I showed, I think, on the first slide that had code. And so now we can sort of break this down a little more and see how it corresponds to things in that protocol specification. This is a function draw frame. It takes an argument, which is, we called it channel, and it's basically an endpoint. And that type there says it's in the acquire state, and the fact that it says client means that this is basically each protocol has a client and a server, and so this is the client perspective, which is what we write everything from. So in the client case, we're allowed to receive. Somewhere there would be other code which describes the server side of this, and they would get a double buffer server acquire object, and they can receive from that. Okay. So I mentioned we generate functions to send messages. Here's an example of that where we generate the request function, which sends a request on the channel. And then, so request consumes the channel endpoint, and it gives you back another channel endpoint. So a lot of times when you're writing code that's in the style, you'll say like let channel equal something of channel, followed by let channel equal something of channel, and so on. Because we can't use channel once we've sent on it, but then we get a new channel that we can use to continue the protocol. So in this case, when we send a request, it was supposed to transfer, or the protocol steps into the wait buffer state, and so we get a new endpoint out that we store in channel, and then we do this to the select is basically receive in this case because we're only selecting over one, but this is receive a message from the channel that we just got, and then we do pattern matching on that. And so this sort of mirrors the syntax for describing a message format. So we say we want to match the give buffer message, and it's going to have a buffer, so we want to bind that to a variable. And then it's also, there's going to be some next state for the protocol because it continues, and so we're going to call that next state channel. So we're rebinding channel again to the next state of the protocol. And then render is a function that takes a reference to the buffer and draws into it. And when that's all done, we call release to send the return, or the message to return the buffer to the server. So are there any questions so far on this? Just sort of an understanding the code? Okay, cool. So that sort of gets into the safety of it because we have this statically checked communication protocol to make sure you're sending messages at the right time and receiving the right messages when you should and getting the right types and all that. But the other thing is we want it to be fast, right? So I did a bunch of benchmarks, or well, I'm going to talk about 3 of them, I guess, and I was pretty happy with how they turned out. It turns out because a side effect of having this protocol specification is that not only does the compiler make you be careful about how you're doing your communication and that you're actually following the protocol you said you would, the compiler then can then assume that you're following the protocol, and it can generate faster code than it would in a more generic case. And so in particular, we know in every case we have one sender and one receiver at every point, and we know who they are, which makes synchronization a lot easier. And in some, at least in the fast path where the send completes before the receiver tries to receive it, we can do this whole thing without any locking in there, which gives us quite a bit of performance. So the first benchmark I want to talk about is this one we called message send ring. And this is a benchmark I wrote earlier in the summer, and it was specifically crafted to make my new system look good. So the old system, we didn't have maybe the best implementation we could have had. And in particular, every time any task anywhere in the system sent a message, there was a global lock we had to acquire and release. Which means basically all the threads get serialized through message sending, which just isn't very scalable. And so that was like one of the first goals, was to make sure we don't have any sort of global synchronization, that any synchronization that happens on message passing only involves the 2 tasks that are exchanging messages. So the idea is these blue boxes all represent tasks. We start up a bunch of tasks, they arrange themselves into a ring, then everyone sends a message to the right, and then everyone receives a message from the left, and then we just go back and forth for a while. And basically we time how long that takes. So there's a lot of messages going back and forth here, but none of them actually conflict with each other, which means that if we did have a global lock that every message had to acquire, we're going to be hitting that lock really, really hard, whereas without it, it should be pretty fast, right? So here's the performance chart. I forget exactly how many, it's like 10,000 messages or so. The old system took close to 4 seconds, and the new system takes under half a second. So this is about a 8x speed up. So I was pretty happy with that. Earlier in the summer it was like 17x, but I was being a little sloppy on the synchronization, and so getting rid of all the race conditions made it slower, but it's still significantly faster than what we had before. The other thing we can do with these protocols is they give us an idea of how much buffer space we need. So under the old system, we just assumed that like a sender could send and send and send and send and send all they want, and we don't know if the receiver is ever going to receive it or not. Whereas some of these protocols that we give now, you can tell just by looking at the protocol that the sender will not go any further until the receiver's received all the messages. So I call this bounded versus unbounded. And so an example, the first protocol I talked about, or the one I've been talking about through most of this talk, that's a bounded protocol. And the way you can tell it's bounded is because all of the loops that are in the protocol, they have to cross both a send and a receive state. Which means that there's no way the sender can just like race way far ahead and send a ton of messages without waiting for the receiver to receive. Because in this case, if we send a request message, we can't do anything else until the receiver receives it and sends you something back. On the other hand, we could have done our protocol like this, where you just had this drawing straight, and to draw a frame, you just send a message that says, here's the new frame, show this on the screen. And if we do this, this is unbounded, because there's nothing to stop the drawing side from just doing this, which is drawing a frame over and over and over and over and over again. And if the graphics card is slow, we could potentially have to buffer up a lot of frames to show up in there. And so in this case, we would have to be able to allocate memory. In the case where we have a bounded protocol, we can actually get rid of all the memory allocation and just say, as soon as you start this protocol, we know how much space the thing could ever possibly use. And so we allocate all the space that we need, and then we never allocate any more again. And so that should make things faster, right? And so to test this, I use just a really simple ping pong protocol. So you have two tasks. They send a message, they wait for it to come back, and then they just go back and forth for a while. And then we count how long that takes. And so we compare this with both a protocol that doesn't do the bounded optimization. So it has to allocate every time it sends because it needs more buffer space. And then there's the bounded example where we don't do any allocation ever once you start up the communication. So once again, this was faster, which is good. Although only by about 9% or so. So it's worth doing, but it's a smaller change, and that's generally a sign that you're doing something right when you start only seeing like 10% performance improvements rather than like 800%, because that usually means you did something wrong to start with if you are able to do 800%. So anyway, so this is one of the optimizations we do, and it pays off pretty well in this case at least. These have both been sort of micro benchmarks so far. And so we don't know, basically what we've seen so far is that I can construct tasks that make my code look really good, or benchmarks that do that. But we don't know how well this pays off in sort of real world applications. And so another program I wrote earlier in the summer was a parallel breadth first search through a graph. And so once I had that, I compared the old version versus the new version and wanted to see how well, whether basically this faster message passing actually makes any real world performance difference in something that's mostly compute bound rather than just testing just the message passing. So we're probably mostly familiar with breadth first search, but just in case, here's how it works. Here's a graph. And we pick some node as the root, so I've chosen the one in the lower left. And we say that this one is in level 0, so it's the first one we see. And then the next iteration, we do the ones that are reachable from that. Then we do another one to the ones that are reachable from there, and so on. And now we've sort of labeled all of these with a number, so we know what order you end up visiting those nodes in. And when you're all done, you can also create a tree so that you can remove the extra edges, and then you have a breadth first search tree. And so the idea behind breadth first search is to produce this tree from an arbitrary graph. Okay. And so comparing the performance of this using the old ports and channel system in Rust versus the new one using channel contracts, here's about what it looks like. So again, on sort of a real-world application, things get faster. I think that's roughly 15% or so difference on there. So again, not the amazing 800%, but it's ideally we're spending most of our time computing, and so the fact that making message passing can give a measurable improvement in performance is still pretty worthwhile. So anyway, that's basically what I had as far as the channel contracts. So we looked at a way of providing safer communication in Rust, in that now the compiler can verify that you're following a protocol, and then we can also use that to get higher performance through some of the static guarantees that we have in there. So thanks, and we'll take any questions right now. All right. Ben.
You mentioned that on the fast path, when a send happens before a receive, no locking is needed. Isn't it true that the sender needs to do just one atomic swap in all cases?
Yeah. So so Ben's question was, I said on the fast path, so the fast path is the send completes before the receive starts. And so the question was, all right, I claimed that there were no locks on that path, and Ben says, don't I need an atomic operation? So the answer is yes. I guess I wasn't counting atomic operations as a lock, but yeah.
How many of those do you need?
On the fastest version of it, there's one atomic operation on the send side and no atomic operations on the receive. And then there's like several slightly slower fallbacks that you go through if any of this fail. So, but in the best case, it's one atomic operation. Anything else? All right. Well, thank you.